You are moving right now. Not metaphorically, not in some poetic sense. Physically. At this exact moment, you're traveling at about 230 kilometers per second. That's roughly 828,000 kilometers per hour. And you've never stopped. Not once, not for a single second of your life. You're orbiting something 26,000 light years away, something you've never seen, something most humans who ever lived didn't even know existed. And it's not just you. Every person alive right now is doing this. Every person who ever lived did it too. Your parents, their parents, every ancestor stretching back through all of recorded history and beyond. Every star visible in the night sky is doing it. All 200 billion stars of the Milky Way, the gas clouds between them, the dust, the planets, the debris, all of it moving in these vast, slow curves around the same invisible point. At that point sits a black hole. 4 million times the mass of our sun compressed into a space smaller than the distance from Earth to Mercury. And for most of human history, for nearly all of it, we had no idea it was there. We looked up at the band of the Milky Way stretching across the sky and saw light. Just light. Beautiful, diffuse, ancient light. And we missed what was holding it all together. If you enjoy calm, careful explorations like this one, space, time, things that are genuinely hard to wrap your head around, consider liking the video and subscribing. It's a small thing, but it's actually what keeps this channel going. Tonight, we're going to trace the story of Sagittarius A star, how we found it, what it is, what it means that we've been circling it forever without knowing. And maybe, though I want to be careful here, what it feels like to finally see the thing you've always been bound to. This isn't a simple story. Some parts of it are strange in ways that don't resolve neatly. The science is solid, but the implications sit with you for a while. So let's take it slow. Let's begin. Part 1. The darkness at the center. For a long time, we couldn't see the center of our own galaxy. Not because we weren't looking, we were. But the Milky Way has a way of hiding things. Between us and the galactic center lie enormous clouds of gas and dust, dense enough to block visible light almost completely. If you point an optical telescope toward the constellation Sagittarius, where the center sits in our sky, you don't see a bright core. You don't see anything particularly special, just stars in the foreground, a few dark patches, the usual scatter of light. The actual center is invisible, completely obscured. And this wasn't a temporary problem waiting for better telescopes. It was a fundamental one. Visible light simply can't pass through that much material. So for centuries, we knew we lived in a galaxy. We knew it had a center somewhere. We assumed it was probably denser than the rest. More stars, more light, more activity. But we couldn't see it directly, and most astronomers figured it was more or less just a crowded region. Nothing exotic. A concentration of ordinary stars packed tighter than average. That assumption seemed reasonable. It was also wrong. The shift came in the 1970s, and it came quietly. Radio telescopes, instruments that detect radio waves rather than visible light, had been scanning the sky for years. Radio waves behave differently than light. They pass through dust. They pass through gas. The same clouds that make the galactic center invisible to optical telescopes are essentially transparent to radio observations. And when astronomers turned radio telescopes toward the galactic center, they found something that didn't fit. A compact radio source, unusually bright, unusually concentrated. It wasn't spread out the way a gas cloud would be. It wasn't moving the way a star cluster would. It was just there, sitting at the center of the galaxy, emitting radio waves with an intensity that didn't match any ordinary explanation. In 1974, astronomers Bruce Ballack and Robert Brown identified it formally. They called it Sagittarius A star, after the constellation in which it appeared. The asterisk, pronounced star, was a notation from radio astronomy, but it stuck. Sgr A star, a name for something whose nature was, at that point, genuinely unclear. What was known, something massive was there, something compact, something that was affecting the region around it in ways that went beyond normal stellar activity. What was not known, almost everything else. The leading hypothesis was a black hole, but a hypothesis isn't evidence. And in science, especially for something this extraordinary, evidence takes time. It's worth pausing here for a second, because I think this part of the story gets glossed over. We're talking about the center of our own galaxy, the place everything we know orbits around. And in 1974, after centuries of astronomy, after Galileo and Hubble and all the rest, we still had no real idea what was there. We had a radio signal and a name. That's not a failure of science. That's just how science actually works. You find the signal first. The explanation comes later, slowly through instruments that don't exist yet and observations that take decades to accumulate. The gap between discovery and understanding is usually longer than we remember. In the case of Sagittarius A star, that gap was about 30 years. Part 2. The stars that explained everything. In the early 1990s, two teams of astronomers decided to do something that sounded almost impractical. They were going to watch individual stars near the galactic center, not survey the region, not map gas clouds or measure radio emissions. Watch specific stars, year after year, and see where they went. The teams were based on opposite sides of the world, one at the Keck Observatory in Hawaii, led by Andrea Ghez, the other at the Very Large Telescope in Chile, led by Reinhard Genzel. They were, in a sense, competitors, working on the same problem with similar instruments, neither fully knowing what the other would find. Both teams used infrared cameras because infrared light, like radio waves, can penetrate the dust between us and the galactic center. Not perfectly, but enough. Enough to resolve individual stars in one of the most crowded, chaotic regions of the sky. And then they waited, season after season, image after image, building up a record of where each star was and where it moved. What they saw, gradually, was motion, not the slow, barely perceptible drift you'd expect from objects tens of thousands of light-years away. These stars were moving fast, visibly fast, even across the timescales of a human research career. And the motion had a shape, curved, elliptical, like objects in orbit, like something was pulling them. The question was what? To bend a star's path that sharply, to make it curve and accelerate the way these stars were curving and accelerating, you need mass, enormous mass, concentrated in a very small region. The teams started calculating. They looked at the sizes of the orbits, the speeds, the periods, and the numbers kept pointing to the same place. Whatever was at the center of these orbits was almost unimaginably dense. One star became the center of attention. Both teams were tracking it. They called it S2, a designation that sounds underwhelming for something that would turn out to be one of the most important stars in the history of astronomy. S2 is a blue-white star, a few times more massive than our Sun. Unremarkable in almost every way, except for where it lives and what it does. It orbits Sagittarius A star once every 16 years, which sounds like a long time until you consider what it's orbiting and from how far away. Our Sun takes approximately 230 million years to complete one orbit around the galactic center. S2 does it in 16. That's not a small difference. That's the difference between a leisurely walk around a city and running a sprint around a track. The orbit is tight. The speed is extreme. At the closest point in its orbit, astronomers call this periapsis. S2 gets within about 17 light-hours of Sagittarius A star. For context, Neptune is roughly 4 light-hours from our Sun. S2 swoops closer to a black hole than Neptune is to the Sun, and at that distance, it's moving at somewhere between 2 and 3% the speed of light, around 7,000 to 8,000 kilometers per second, fast enough to cross the distance from Earth to the Moon in under a minute. The teams watched S2 complete a full orbit. It passed periapsis in 2002, then again in 2018, 16 years apart, almost exactly. And between those two passes, every data point, the acceleration going in, The deceleration coming out, the shape of the ellipse, matched what you'd expect from an object orbiting a single massive point source. This is where the math became decisive. To produce an orbit like S2's that tight, that fast, you need roughly 4 million solar masses concentrated in a region smaller than our solar system. The teams ran the numbers independently. They got the same answer. Then they started ruling out alternatives. Could it be a dense cluster of stars? Possibly. But a cluster that massive in that small a space would collapse under its own gravity almost immediately. It wouldn't last long enough for us to observe it. Could it be some exotic form of matter we haven't cataloged? Maybe, in principle, but there's no theoretical framework that supports a stable object of that density that isn't a black hole. Could it be something else entirely? Something outside our current models? That's always a possibility in science, but you don't invoke unknown physics when known physics already fits the data cleanly. The data fit one thing: a supermassive black hole. 4 million solar masses sitting at the center of the Milky Way. By the early 2000s, the case was effectively closed. Genzel and Ghez would eventually share the Nobel Prize in Physics for this work in 2020. But the real moment, the moment the evidence became undeniable, was quieter than a Nobel Prize ceremony. It was a graph, a plotted ellipse, a star's path traced across decades of infrared images, curving around an invisible point. That invisible point was Sagittarius A star. And it's worth saying, none of this required a photograph, no direct image of the black hole itself, just stars and the invisible curves they traced over decades of patient watching. The evidence was entirely indirect and entirely conclusive. Part 3. The first image. For decades, we knew Sagittarius A star was there. We could measure its mass, track the stars around it, map its gravitational influence across light years. But we'd never actually seen it. A black hole, by definition, doesn't emit light. You can only image the region around it, the hot gas, the distorted space, the boundary where light stops escaping. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole. It was M87 star, a giant at the center of a galaxy 55 million light-years away. A blurry orange ring with a dark center. Not pretty in the conventional sense, but scientifically extraordinary. Proof that what the equations predicted actually existed in the form we expected. Sagittarius A star came next, and it was harder. M87 star is about 6.5 billion solar masses. It's enormous, and it changes slowly. Gas takes days or weeks to orbit it. Sagittarius A star is smaller, and the gas around it moves on timescales of minutes. The image kept shifting while they were trying to capture it. One researcher compared it to trying to photograph a child who won't sit still, except the child is 26,000 light-years away, and the exposure takes years. The EHT is not a single telescope. It's a network of radio observatories across the planet. Chile, Hawaii, Arizona, Mexico, Spain, the South Pole, synchronized to act as one Earth-sized dish. The team combined years of observations, compensated for atmospheric distortion, accounted for Earth's rotation, and assembled the image computationally, piece by piece. In May 2022, they released it, a bright ring of gas bent into a circle by gravity, a dark center, the shadow of the event horizon. Fuzzy, uncertain at the edges, but unmistakably real. And here's the thing that struck me about it. Sagittarius A star looked quiet. Not a raging quasar, not a jet of plasma shooting across space. Just a ring, a dark circle, something enormous and almost completely still. We'd spent decades imagining the center of our galaxy as something violent, What we actually photographed was closer to dormant. Part 4. What 4 million solar masses actually means. 4 million solar masses. The number gets repeated a lot in articles about Sagittarius A star. It's worth actually sitting with it for a moment, because it's the kind of number that sounds large without feeling large. Start with our Sun. It's about 1.4 million kilometers across. It contains 99.8% of all the mass in the solar system. Every planet, moon, asteroid, and comet combined makes up the remaining 0.2%. The Sun is, by any everyday standard, incomprehensibly massive. Now compress it into a black hole. Its event horizon would be about 6 kilometers across, a sphere you could drive around in a few minutes. Do that 4 million times. Crush all of it into a single point. That's Sagittarius A star. The event horizon, the boundary of no return, is roughly 24 million kilometers in diameter, about 17 suns laid side by side. Light moving at 300,000 kilometers per second takes about 80 seconds to cross it. A minute and 20. That's the edge. Past that edge, our normal descriptions stop working, not because we lack imagination, but because the physics genuinely breaks down. The equations that describe gravity, which work everywhere else we've tested them, predict a singularity at the center, a point of infinite density. Most physicists suspect that's a sign the equations are incomplete, not that infinity is literally there, but we don't have a better description yet. For scale, Sagittarius A star contains roughly 1.3 trillion Earth masses, and by the standards of supermassive black holes, it's actually modest. M87 star, the first black hole ever photographed, is 6.5 billion solar masses, more than 1,000 times more massive. Ton 618, one of the largest known, sits at around 66 billion. Next to those, Sagittarius A star is almost small. Almost. Part 5. The 26,000-year delay. Here's something that doesn't get mentioned enough when people talk about Sagittarius A star. Everything we know about it is old. Not old in the way that historical records are old in the way that the information physically cannot be newer. Light travels at roughly 300,000 kilometers per second, and that's it. That's the speed limit. Nothing carries information faster, which means that the light reaching our telescopes from Sagittarius A star left there 26,000 years ago. The image released in 2022, the one that made headlines that took years to assemble, shows Sagittarius A star as it existed during the Upper Paleolithic. When the image we photographed was actually happening, humans were living in small nomadic groups. Cave paintings were being made in what is now France and Spain. The first cities were still 10,000 years away. Writing didn't exist. Those photons left the galactic center, traveled through 26,000 light-years of space, passed through dust clouds and Spiran arms and the quiet emptiness between stars, and finally landed on our radio dishes. And we called it a photograph of Sagittarius A star. It is, but it's a photograph of the past. There's no way around that. What is Sagittarius A star doing right now at this actual moment? We can't know. The light that would tell us won't arrive for another 26,000 years. By then, if anyone is around to receive it, human civilization will be unrecognizable or gone. The stars in the night sky will have shifted, the continents will have moved. This isn't a poetic observation, it's a hard physical constraint. We are separated from Sgr A star not just by distance, but by time. And those two things, out here, are the same thing. But even across that gulf, even knowing we can only ever see the past, we've managed to understand something real about how Sagittarius A star works, what it does, how it holds things, and what it means that we're among the things it's holding. Part 6. Orbits and the Dark Anchor. Right now, our solar system is moving through space at 230 kilometers per second, a number we mentioned at the very start of this video. But it's worth returning to it here because it means something different once you understand the scale of what we're orbiting. At that speed, one full orbit around the galactic center takes approximately 230 million years. The distances involved are just that large. The last time our solar system occupied this exact position in its orbit, the Triassic period was just beginning. Dinosaurs hadn't appeared yet. The continents looked nothing like they do now. We've completed exactly one lap since then. One! And in that time, entire branches of life evolved, dominated the planet, and disappeared. Stars closer to Sagittarius A star move faster. S2 completes its orbit in 16 years. S62, another tracked star near the core, has an orbital period of roughly 9.9 years and reaches nearly 10% the speed of light at periapsis. These aren't outliers, they're just what happens when you get close enough to 4 million solar masses. Further out, the timescales stretch. Stars at the galaxy's edges take hundreds of millions of years per orbit. Some have been circling since before our solar system existed. They'll still be circling long after the sun burns out. All of them, S2 screaming around at relativistic speeds, our sun on its 230 million year crawl, the slow stars at the outer edges, bound to the same point, the same invisible object. Sagittarius A star doesn't hold the entire Milky Way together on its own. Dark matter, stellar mass, gas, all of it contributes. But at the center, its gravity dominates. It sets the rhythm for everything near the core. It's been doing this for billions of years, quietly, without variation. So here's where we end up. There's a black hole 26,000 light-years away. You can't see it. You can't point to it in the night sky with any confidence. It sits behind so much dust and gas that even knowing exactly where it is, your eyes find nothing there. And yet you've been orbiting it your entire life. Every night you've ever spent outside looking at the stars, you were moving around it at 230 kilometers per second. That's a strange thing to absorb. Not frightening exactly, just strange. What I keep coming back to is the delay. The fact that everything we know about Sagittarius A star is 26,000 years old. The image, the orbital data, the radio signals, all of it ancient by the time it reached us. We built instruments, spent decades observing, assembled one of the most complex scientific collaborations in history, and what we captured was a picture of something as it existed during the Stone Age. Maybe that's just the nature of looking outward. You're always seeing the past. The further you look, the older the light. In a sense, every telescope is a time machine running in one direction only, and you never get to see anything as it actually is right now. You see what was. You infer what might be. Whether Sagittarius A star is doing something interesting at this exact moment, flaring, pulling in a gas cloud, quiet as it usually is, we won't know for 26,000 years. That gap doesn't close. It's not a problem to be solved with better technology. It's just the shape of the universe we live in. And somehow, despite all of that, despite the invisibility, the distance, the delay, it holds. It has always held. Every orbit, every star, every slow revolution of the galaxy around that dark center. Patient in a way that has nothing to do with patience, because patience implies waiting for something. Sagittarius A star isn't waiting. It just is. You're still moving, by the way. You were moving when you started watching this. You'll be moving when you stop. If this kind of exploration feels worthwhile to you, a like and a subscription genuinely help this channel keep going. There's a lot more of the universe left to look at. See you in the next video.